In the cold, distant reaches of our solar system, a tiny world named Pluto holds a truly remarkable secret. For many years, we thought of it as little more than a frozen, inactive ball of ice and rock, orbiting far from the sun's warmth. But when NASA's New Horizons spacecraft flew past in 2015, it sent back pictures that changed everything. The images revealed something entirely unexpected, a stunning, multi-layered blue haze wrapping around the dwarf planet. This wasn't just a simple atmosphere, it was a complex ethereal veil that hinted at processes we were only beginning to comprehend, a sight that transformed our view of this remote world forever. The discovery of this haze was a moment of pure scientific wonder. As New Horizons looked back at Pluto, with the sun illuminating it from behind, it captured the silhouette of the dwarf planet surrounded by this delicate glowing halo. The haze extended far higher than any models had predicted, reaching over 185 miles or 300 kilometers above the icy surface. It was a beautiful but deeply puzzling observation. Scientists knew that haze could form on other worlds, but Pluto's was so extensive and structured that it posed a significant challenge. How could such a cold, tiny world with such a thin atmosphere sustain something so magnificent and complex? It was a question that would require a new generation of technology to answer. The creation of this beautiful blue shroud begins with the fundamental building blocks of Pluto's thin air, nitrogen and methane. Even though Pluto is incredibly far from the sun, the faint sunlight that reaches it is just powerful enough to trigger chemical reactions. Ultraviolet light from the sun strikes the methane gas molecules in the upper atmosphere, breaking them apart. These broken pieces then recombine into more complex molecules, forming tiny particles of hydrocarbons and nitriles. Over time, these small particles stick together, growing larger and heavier, slowly sinking down through the atmosphere like a very fine cosmic dust. It is these tiny suspended particles that scatter sunlight, creating the distinct blue color we see. This process is what makes Pluto's atmosphere visibly glow, but it's more than just a beautiful spectacle. The existence of this haze suggested that it must play a crucial role in the planet's overall system. Early theories proposed that the haze might be interacting with the energy from the sun in a unique way, but confirming this was impossible from Earth-bound telescopes, or even with the data from New Horizons alone. The haze was a clue, a signpost pointing towards a new kind of climate, one governed not by gases as on Earth or Mars, but by these tiny floating specks of organic matter. The stage was set for a deeper investigation, one that would need the most powerful telescope ever built. To truly understand what was happening in Pluto's atmosphere, scientists needed a new tool, one powerful enough to peer into the faint thermal glow of the dwarf planet from billions of miles away. That tool is the James Webb Space Telescope, or JWST. Its incredible sensitivity to infrared light, the kind of light associated with heat, was precisely what was needed to solve the puzzle. However, there was a major challenge. Pluto is not alone. It is accompanied by its very large moon, Charon, which orbits incredibly close. From our vantage point on Earth, the light from Charon often contaminates the signal from Pluto, making it nearly impossible to get a clear reading of Pluto's faint atmospheric heat. The breakthrough came with JWST's mid-infrared instrument, or MIRI. This instrument is so precise that it was able to separate the light coming from Pluto from the light coming from Charon, a feat that had been impossible before. For the first time, scientists could isolate the thermal signature of Pluto's atmosphere and measure its temperature with incredible accuracy. As Tanguy Bertrand, a lead researcher on the project, explained, this was the key that unlocked the mystery. The observations confirmed what some scientists had hypothesized after the New Horizons flyby. The haze was not just a passive feature, but the main driver of Pluto's climate. The findings from JWST were astonishing. The data showed that Pluto's upper atmosphere was much colder than our models had predicted, by about 17 degrees Celsius or 30 degrees Fahrenheit. The temperature was a frigid minus 203 degrees Celsius or minus 333 degrees Fahrenheit. This result was a direct confirmation that the haze was actively cooling the atmosphere. It works a bit like a planetary-scale air conditioner. The tiny haze particles are very good at absorbing heat from the distant sun during Pluto's long day, but then they efficiently radiate that heat back out into the cold vacuum of space as infrared energy, preventing it from ever warming the atmospheric gases below. This confirmation was a huge moment for planetary science. As scientist Shi Zheng noted, it's not often that a major hypothesis is confirmed so quickly, within just a few years of its proposal. The journey began with the tantalizing images from New Horizons in 2015, which gave us the first hint of this strange climate. Then, armed with a theory but lacking definitive proof, scientists had to wait for the launch and commissioning of JWS. The data it provided in 2022 was the final piece of the puzzle, providing concrete evidence for a climate system that is, as Tanguy Bertrand put it, unique in the solar system. It was a perfect example of how different missions built decades apart can work together to reveal the universe's secrets. So what does it mean to have a climate controlled by haze? On Earth, our climate is primarily governed by the gases in our atmosphere, especially greenhouse gases like carbon dioxide and water vapor. These gases trap heat from the sun, keeping our planet warm enough for life to thrive. This is the case for most planets with substantial atmospheres, but Pluto is different. Its atmosphere is incredibly thin, about 100,000 times less dense than Earth's. The few gases that are present don't have enough substance to trap heat effectively. Instead, the haze particles have taken over this critical role, but they do the opposite of what our greenhouse gases do. Imagine the haze as a vast, reflective blanket of tiny mirrors floating high in the sky. During the day, these particles absorb sunlight, but they don't hold on to that energy for long. Instead of warming the air around them, they quickly release the energy back into space as heat radiation. This process acts like a giant cooling system, preventing the upper atmosphere from heating up and keeping the entire atmospheric column colder than it would be otherwise. This is why scientists have called it a new kind of climate. It's an anti-greenhouse effect, where the presence of these organic particles leads to a net cooling, a mechanism we haven't seen dominate anywhere else. This discovery forces us to broaden our definition of what a climate can be. It shows that even on the most distant, coldest worlds, there can be complex systems at play that regulate temperature and energy. The processes on Pluto are a delicate balance. The very sunlight that creates the haze particles is also the energy source that the particles then radiate away. It's a self-regulating cycle that has likely shaped Pluto's environment for billions of years. Understanding this balance helps us appreciate the sheer diversity of planetary processes that can exist across the cosmos, far beyond the familiar weather patterns of our own world. The implications are profound. It means that when we look for habitable or interesting worlds elsewhere in the galaxy, we can't just look for Earth-like atmospheres. There may be countless other ways for a planet to regulate its temperature. Pluto, once dismissed as a simple ice ball, has shown us that small cold worlds can have incredibly sophisticated systems. It teaches us to expect the unexpected and to remain open to the possibility that nature has found solutions to planetary physics that we have not yet imagined. Pluto's haze-driven climate is a testament to the universe's endless creativity. Pluto's unique climate isn't just an isolated curiosity. It provides a vital new lens through which we can view other mysterious worlds in our own solar system. One of the most intriguing parallels is with Saturn's largest moon, Titan. Like Pluto, Titan is shrouded in a thick orange-tinted organic haze formed by similar chemical reactions involving methane and nitrogen. While Titan's atmosphere is much thicker and its climate more complex, the fundamental chemistry that creates its haze is the same. By studying the simpler system on Pluto, scientists can refine their models for how these organic hazes form and behave, which in turn helps us better understand the much more complex environment of Titan. Another celestial body that comes to mind is Neptune's moon Triton. When the Voyager 2 spacecraft flew past Triton in 1989, it revealed a thin atmosphere and plumes of dark material erupting from its icy surface, suggesting geological activity. Triton is widely believed to be a captured object from the Kuiper Belt, just like Pluto, and likely shares a similar composition. The discovery of Pluto's haze-controlled climate strongly suggests that Triton might have a similar system. It gives scientists a new framework for re-examining the old Voyager data and for planning future missions, knowing now what kind of climate to look for on these distant icy bodies. Perhaps most fascinating of all, Pluto's haze may offer a glimpse into the distant past of our own planet. Billions of years ago, before the rise of oxygen, early Earth's atmosphere was very different. Some scientists believe it may have been shrouded in a similar organic haze, created by sunlight acting on methane produced by early life. This ancient haze could have played a crucial role in Earth's early climate, possibly shielding the surface from harsh, ultraviolet radiation and helping to stabilize temperatures. By studying Pluto, we are, in a sense, looking at a potential analogue for the conditions that may have existed on our own world long ago, before it became the blue marble we know today. Ultimately, the discovery of Pluto's haze-driven climate is a powerful reminder of why we explore. Each new world we visit shatters our old assumptions and expands our understanding of the universe. Pluto has transformed from a point of light in our telescopes to a complex and dynamic world with a climate all its own. This knowledge enriches our cosmic perspective, showing us that the universe is filled with a greater variety of environments than we ever imagined. It underscores the value of scientific curiosity and the incredible power of our instruments to reveal the secrets of even the most distant corners of our solar system.